you very much. Today I'll talk about my PhD dissertation called Enabling Efficient and Scalable DRAM Read Disturbance Mitigation via new experimental insights into modern DRAM chips. So I'll start with the concept of lack of memory isolation. Imagine that this is your memory and you perform an access to a particular location in your memory and you observe a data, a bit change in another location. So you do not want this to happen because it might lead to data loss or corruption. It can compromise your application's correctness. It can be used against you to leak your private information or take over your computer. So data integrity and confidentiality issues may emerge as a result of this. This is a really simple principle, but unfortunately today in modern memory chips, it's difficult to satisfy. And here's why. So as the prevalent memory technology, we use dynamic random access memory or DRAM. And DRAM stores data in the form of electrical charge on a capacitor, and it's a leaky circuit, so it needs to be periodically refreshed. There is this phenomenon called DRAM read disturbance, where access in a DRAM cell disturbs other physically nearby cells and exacerbates their charge leakage. Rowhammer is a prime example of DRAM read disturbance. So here we access DRAM cells internally in DRAM row granularity. So assume that we access data in row 2, so we need to open or activate row 2. And once we are done with this and we want to access another data in another row, we need to close it. When we do this open and close operation many times, we observe bit flips in physically nearby rows that are not necessarily accessed. And this breaks the memory isolation and leads to all those problems. With technology, manufacturing technology advancements and DRAM chips getting denser, we have smaller cells and cells are getting closer to each other. As a result, read disturbance vulnerability increases a lot. And existing solutions become prohibitively expensive or ineffective going forward. And to find better solutions, we believe that we need a more detailed understanding of DRAM read disturbance. And major contributions of my thesis towards the goal of efficient and scalably mitigate DRAM read disturbance are first, we build a detailed understanding of DRAM read disturbance. To this end, we look at Rowhammer sensitivities with varying temperature, memory access patterns, victim cell's physical location, and voltage. Second, we use these insights and we build on them to devise novel solutions and leverage insights into DRAM chip internals and memory controllers. To this end, we propose mechanisms that leverage heterogeneity in Rowhammer vulnerability across DRAM cells and rows. We propose methods of parallelizing preventive actions so that we reduce their performance overheads, and we propose a mechanism that selectively throttles unsafe accesses to prevent bit flips. So due to time limitations, I'm just going to talk about 2 of these topics. But first, I'd like to introduce you my testing infrastructure. So this is an FPGA-based infrastructure which we program with our own design called DRAM Bender. DRAM Bender is open source today and available on GitHub, and it supports multiple FPGA boards and DRAM standards. So in this FPGA board, we plug in a DRAM module that we get from the retail store, and this infrastructure is connected to a host machine to run the tests, and we clamp the DRAM module with heater paths from both sides that are controlled with a commercial temperature controller so that we can control the temperature on the chips. And we have a power supply on the side that allows us to play with the voltage on certain power rails. So this infrastructure gives us fine-grained control over DRAM commands, timing parameters, temperature, and voltage. And this infrastructure, we built this infrastructure for different DRAM standards, including DDR3 SODIMMs, DDR4 RDIMMs, UDIMMs, DDR4 SODIMMs, and HBM2 DRAM chips. And we conduct similar experiments on all of them. But in the set of experiments that I'm going to share, we test 272 DRAM chips from 4 major manufacturers that implement different densities, die revisions, and chip organizations. And to characterize our DRAM chips in the worst case conditions, we do the best effort to prevent sources of interference during our core test loop, and we perform the worst known access sequence. So I'll talk about 2 aspects of this because of the time limitations only. First one is temperature, the second one is memory access patterns. Let's begin with temperature. So in this study, we sweep temperature from 50 degrees Celsius to 90 degrees Celsius, and we keep testing our chips to observe any Rowhammer-related bit flips. We observe a lower bound of temperature and an upper bound of temperature. In between, a DRAM cell experiences bit flips, and outside of this temperature range, it doesn't experience bit flips. So So we call this temperature range vulnerable temperature range, and we observe that vast majority of the vulnerable DRAM cells are vulnerable to row hammer in a bounded continuous temperature range. Here's the population density distribution as an example. So on the x-axis we have the lower bound, and on the y-axis we have the upper bound of the vulnerable temperature range, and each data point shows the fraction of DRAM cells that fall into that vulnerable temperature range. For example, 4.3% of the cells here exhibit row hammer bit Phillips only between 50 degrees Celsius and 60 degrees Celsius, but not above or below it. This has an immediate implication on testing. Now you cannot just crank up your temperature to 90 degrees Celsius and expect to observe the worst case. You need to test your DRAM, each DRAM cell in each possible operating temperature to make sure that you're not vulnerable to row hammer. And it motivates future research on low-cost testing methodologies. Second aspect is memory access patterns that I want to talk about. So before our study, the worst known access pattern was opening and closing DRAM rows or activating DRAM rows as frequently as possible to maximize the activation count in a limited time window. Instead of doing that, what we did is, whenever we open a row, we kept it open for a longer time. And there are some reasoning in the circuit level, but I'm not going to get into that. And when we do this, we observe that we can achieve bit Phillips at significantly smaller hammer counts. And this also has an immediate implication on defense mechanisms. If your deployed defense mechanism in your computer does not account for this kind of effect, you can play with the access pattern and bypass your defense mechanism. And more importantly, this finding paved the way to the discovery of row press, which is a new redisturbance phenomenon. Here we can see the effect of it. So on the leftmost side, we have the row hammer attack, and on the x-axis, we increase the time that we keep the row on for a longer time. And as we go from left to right, we go from row hammer to row press. And as you see, the necessary activation count to induce bit Phillip drops 1 or 2 orders of magnitude. And in extreme cases, we can achieve bit Phillips only with 1 activation. And when we try this with HBM2 devices later on, we also observe very small activation counts to get a bit Phillip. And this activation count is small enough that the benign workloads also achieve this kind of activation count. And it also had a place in media, and we also now have some official announcements that manufacturers are implementing measures against row press. And our studies repeatedly showed that row hammer is an important and complex problem. And last year, even JEDEC released the first promising update after a decade after the discovery of row hammer. So in this thesis, I have some other works that I cannot cover now, but collectively they provide a strong foundation for secure memory systems while DRAM chips get more and more vulnerable, and they highlight the importance of and impact of testing real DRAM chips and motivate new research avenues for testing real DRAM chips. And with this, I conclude my talk. I'm happy to get your questions. Thank you very much.
So you showed that if you keep it open for longer, you need fewer activations, right? But if I look at the total time, right, you had kept on toggling it, would you see a similar number of flips in the same amount of time?
It can be similar. You might need longer attack time as well. But the key is your defense mechanisms are configured based on the activation count. Even if it takes longer to perform the attack, since your activation count is lower, you can bypass them.
Any other questions? Quick questions? Okay, let's thank the speaker. Thank you, everyone.